right, hello everyone. My name is Melchior. I'm working at Swisscom. And at Swisscom, in my team, we are building the monitoring platform for Swisscom. So it ranges from emergency phone numbers to banking, military, government, all the private customers, business customers, all of the 1,300 applications that we have at Swisscom, managing different things. And in this context, we are working for internal customers, so mostly the service control center of Swisscom. So they are working 24/7 to monitor, receiving our alerts, using our dashboards and everything that we built for them. And also the DevOps teams of Swisscom. So every single software engineering DevOps team at Swisscom is also using this platform, as well as the business stakeholders who would like to know a bit where things are breaking. So in this context, I'm not going to present the whole platform. I chose to present to you guys a subset of this platform. And the topic is automated root cause analysis. So let's start with a bit of context. Let's say a Swisscom customer interacts with Swisscom in some way at a shop or something. Who here is a Swisscom customer? Wow. Tough crowd, all right. It's okay, I'm not here to sell. So let's say you go online to buy some mobile subscription or anything, or go to some shop, and that customer is going to interact with some website, and this website is going to trigger some other backend somewhere at Swisscom to do some other action. And this in turn is going to trigger usually another backend, another system. And this is going to be a chain of interactions until at some point the customer's request is fulfilled. You can imagine, for example, ordering a new router for your home. An order is placed at the post to deliver this router. That means the order is placed. And there are many steps in between. Like, for example, maybe a service is responsible for checking if there is fiber access at this location, for example, or if the customer has enough balance to pay for this service. We can define a clear start and end for this interaction from when the customer is requesting something until this order is fulfilled. And this is what we call a top business process. The top business process, we have many. They are defined by the business at Swisscom, and we have about 100 of them. For example, new customer joins Swisscom is TBP number 1. You have buy new mobile subscription. You have also top business processes for B2B, for example, Sunrise renting some fiber access on some line, anything. And Swisscom is mostly interested in monitoring those. They want to know if the top business processes are working or not. And this is quite hard because, well, actually, this top business process is spread across resources. When I say resource, it's a Swisscom internal term. You can think of it as an application. An application, when I say application, it means a team building some specific application using, in general, a microservice architecture. And you can see in this fake example, this top business process is spread across 3 different resources. This means that when something goes wrong in one of those microservices and the whole chain is affected, well, you need to find out where is the root cause, and you need to find it across different teams. So this makes it hard to manage because think of it of every team having a microservice architecture, and the top business process is spread across different teams that need to interact with each other, and you have no clue where the problem is. And this is, of course, a toy example, but about the scale, so about 100 top business processes, about 1,300 different resources. Each resource is about maybe 5 to 10 engineers, and each resource about 20 to 40 different microservices. And each top business process usually involves 30 to 40 different microservices in the chain for a single customer interaction. So in this context, it can be a bit of a nightmare. So at the time where there was a lot more incidents than now, because Swisscom has improved on that, they started with Mosaic. So Mosaic is the name of our platform, and our mission is to provide end-to-end transparency on Swisscom's most important services and processes. That was part at the time of what they called Mission 100 for 2025, 100% availability on all Swisscom services. Of course, not reachable, it's never 100%. And now it's part of some other task force, but the mission has not changed. So how are we going to build that? How did we build that? Let's start with a subset, again, of the platform. It's not everything. I chose a small part. And the first part, maybe many of you guessed it, it's based on distributed tracing. because of course you have many things interacting with each other. So just more recap, when you have microservice A calling B, calling C, every function call is sent to a distributed tracing instance. All the spans are sent and grouped to a trace. This is the general concept, and it allows to trace all the interaction. And you have many technologies nowadays that do this kind of observability, whether it was Zipkin, Jaeger, Tempo now. So you can instrument this in your application using hotel collectors, for example. And currently, the standard at Swisscom, it has changed over the years, but it's Tempo. The difference is that there is not a single Tempo instance, because every single team at Swisscom has their Tempo instance. Of course, there are initiatives to try that everyone has the same technology stack, but there is a lot of very old legacy applications at Swisscom. They cannot all do that. So there is a lot of stuff going on. That's the first, basically, step of our stack, is basically have them all sent to Kafka and source it into our platform. So first step is we receive all the spans and traces from all the applications at Swisscom. They send it once they have instrumented their own application in some way. Once we have this and we receive a certain large amount of spans per second, then we ingest those and we're going to try to monitor that. How do we monitor that? Well, the first step is let's build metrics. So for each microservice A calling microservice B with a certain number of spans per second, this is called a function. So a function between A and B. And for that function, we're going to have streaming jobs building metrics. 3 different metrics. The first one is number of calls. How many spans did we receive per minute? Then the second one, number of errors. And the last one, the P95 duration. With these 3 metrics, we can monitor pretty well the state of a given function between 2 microservices. What are we going to do now with these metrics? So we have 3 metrics, okay? They can go up and down, they can behave as usual. But what is usual? This needs to be learned. So the next thing we're going to do is, well, we dump them to some storage. It's going to stay there for a retention of 2 months, and every morning there is a machine learning model that is going to learn each one of those, I think about now 300,000 time series, and it's going to learn the behavior over the last 2 months. It's going to learn seasonality, trend, noise, everything, and it's going to make a forecast for the next 24 to 26 hours until the next job can run for the same machine learning model. So once we have predictions, well, the next step, obvious step, is anomaly detection. So you're going to have in our front end, this is a screenshot from the front end, so you're going to see basically the observation, meaning what was the metric, and then the borders are what the machine learning model predicted. So it's not predicting a single value, it's always predicting a range, meaning like it says like probably it's going to be between this lower and upper bound. When the observation is within the bounds, all good. When it's outside of the bound, this is called an anomaly. And this we can easily detect. So this is how we can detect in real time anomalies for all of the functions from the spans and traces we receive. All right, so we went now from spans and traces to metrics to anomaly detection. And now the next step is, well, these anomalies, it doesn't mean that there is a problem, right? An anomaly means something unusual happened. Doesn't mean it's a problem. And there are many different types. So the next step is, like, can we build a health score out of this? Because, well, you have different types of anomalies. Maybe it's not the same severity. We have traffic error duration. If you have an anomaly in traffic or duration, maybe not the same kind of severity. Well, different amount of anomalies and, well, different spikes. Maybe if there is a very large spike, it's maybe more severe than if it's a small spike above the bounds. Who knows? So all of this needs to be somehow tuned and aggregated into a health score. So we have spent a fair amount of time tuning many different parameters to try and basically we have a health score, and in our context, we have defined it as a score between 0 and 100. You have unhealthy, warning, healthy with some thresholds. And the idea is that when we receive anomalies for a given function, based on different parameters of the type, the amount, etc., we can build a health score between 0 and 100% and give a state to each function. All right, so now we have a state for each function. What is the next step? Well, we don't want to monitor a single function. This is about the large scale. This is about the top business processes in the end. So we're going to propagate this to the top. So now let me show you just before I jump on how to propagate a bit about the domain model. So the domain model means It's not the full picture, right? We have a lot of other things in the domain model, but for this talk in particular, we have the function at the bottom, right? It means the calls between A and B. And this function always belongs to a component in our stack. When we say component, it means a microservice, a database, an API, anything that has been instrumented by someone. And this component is always part of a resource. The resource is an application, and it has a specific ID because it's part of a Swisscom catalog. At Swisscom, every single application of a team is part of a catalog, and they have a resource. And optionally, each of these components can impact a top business process. They can be part of the chain. So this is the domain model. And now we have a health score for the function at the bottom. And usually there are many functions for different components, for a single component. So imagine you have 3 functions. Each one has a health score based on different anomalies, all right? And we have a way of computing the impact because not every single function, if you have a single microservice, not every function is as relevant as each other, right? They can have different impact on the component. We have a way of computing that, and then we're going to have a simple degradation method, and basically we are able to derive a health score for the component as well. So now, based on the anomalies that are at the bottom for each function, we can propagate this to the component. So the microservice now has a state also, based on the functions, based on the anomalies. And again, we have also other rules to propagate this to the resource and to the top business process. So in the end, the resource and the top business process also have a health score. And this is all derived from bottom to top. And this is key because now I've seen in other contexts the mistake of going top-down, where basically it's also valuable, right, if you have top-level indicators for the top business process or the resource at the top. But if you have an alert on a top-level indicator, what do you do next? I mean, you don't have anything. You're going to have to drill down and look for something. With this, since it's bottom-up, the anomalies are directly from the spans level, all the way propagated to the top. So when the indicator at the top business process is triggering an alert, you have the chain for free, basically, because that's how it was computed. Not to say that we don't have top-level indicators. They are also there. You know, that's another part of the monitoring platform, but this is how we can basically propagate everything to the top. So speaking of going back to the chain, now this goes into the second part of the monitoring. Let me take a step back and talk about the life cycle of an issue. So what happens when you have an incident in Switzerland for Swisscom? So let's say some network segment in some part of the country is down, or Swisscom TV is broken in some areas or something. So first the issue occurs, and then at some point, hopefully, the issue is detected, right, by the service control center. And they're going to start investigating. At some point, they're going to find the root cause. And when they find the root cause, they're going to repair it. Probably many of you know this part. So the first part is called MTTD, so mean time to detect. And the second part is called MTTR, mean time to repair. Both of these are metrics that we try in every monitoring system to optimize. The first part, MTTD, is what I just presented. So you have spans and traces, and in near real time, can we have a health score for the top business process, the whole chains. Spans, traces, through metrics, through anomaly detection, through health score and propagation. And this has gone well. Now the service control center receives alerts and detects in under 30 seconds. So this is near real time. If there is a problem somewhere in Switzerland, in 30 seconds, it's detected by the platform. And the next part is harder, usually longer, the MTTR. It's how do you repair? And what is crucial here is the root cause analysis. So I mean from the time you detect, from the time you find the root cause. Because the last part, the resolution, not in all cases, but in most cases, it's quite fast. Because somebody made a commit and deployed, and if you find that that was the root cause, well, just revert your changes, right? It's not that hard. Not always, right? In networking, sometimes reverting a change can be hard, but let's say the biggest chunk of this time that we want to optimize, because every single minute is costing a lot for Swisscom of downtime, well, it's the root cause analysis. So now that we have this, let's go into a bit of definitions, because when we say root cause analysis, there are different meanings. When I say root cause analysis, I mean the human process of finding the root cause of an issue. And when I say auto RCA, which is the title of this talk, affecting C3. The last part we can build based on distributed tracing. So this we build on the side. Basically, when you receive spans and traces, you can build a database of a graph database, basically, that updates itself based on what it receives. So based on all of that, what we create are graphs. So this is pretty much what it looks like in the front end when you have an issue. And you can see from left to right, deployment was causing some anomalies. Then anomalies are causing function health score to degrade, which are causing components to degrade, then resource, then top business process. And then it means that on a single page and a single view, you can see deployment affected the top business process of Swisscom and is the root cause for that. So this is key to have this as a causal graph and be able to visualize this. And here in this picture, you see only one resource, two components, but we have some graphs that can be larger than that. And of course, then this is a single issue. So it means that now if you link these things, like if you have 4 different teams that are part of the TBP that is affected, they're all going to be part of the same RC issue. It's the same ID, it's the same alerting, it's the same page, it's the same collaboration. So it's not like you have 4 different ITSM tickets spread somewhere, right? It's the same collaboration. So this is key to create this causal graph to have a single entity on which people can investigate and collaborate to go as fast as possible. Now, if you have a graph, that here it's quite small, so you can say, okay, it's fairly easy to say where is the root cause. And if you would think like, how can an algorithm compute what is the root cause here? Well, basically it's a node that has incoming degree of 0, basically. It's a node that has no incoming edge. Well, it's not always that easy because here already we have 2. We could say, okay, deployment, primes over traffic anomalies, okay, fine. But it's not always that nice because usually you have maybe 4 different components that are root cause and which one should we tackle? So it's not, we can go a bit further than that because sometimes the graph is not enough for the service control center to directly pinpoint what is the root cause in the graph. So we need to go a bit of a step further. So next thing we said, well, actually, usually the key information lies in the past. Similar investigation. A lot of these are repeating offenders, and we need to investigate the past. To investigate the past, we need some building block. This building block is called graph similarity. We store these issues, and let's think about, like, if we look at the past, could we compute some similarity between graphs and leverage what was said or found in the investigation about the past issue for the current issue? So we need a graph similarity. And here you have 2 graphs, and you could think like, okay, how are these 2 graphs really similar? F1 is present in both, not the same amount of duration anomalies though. Component 1 present in both. C2 has not the same health score. C3 is present only in 1. Well, how can we say if it's, how well is it similar between those 2? So basically, the point is, let's find a similarity function between 2 graphs. So each issue is basically a set of vertices and edges, and let's find a function that is always between 0 and 1 to find. Many probably think like, yeah, you can do this with graph embeddings quite easily. You convert to vector in the vector similarity. We don't need to do that because you need to train this graph embedding, so it's quite a lot of power and resources, and we can do it simpler than that because we have a topology. So what we did is basically take the nodes, and we have basically weighted average of different attributes on the nodes and edges, and then we pass it to some sigmoid activation function to bump it a bit to the top of the one so that it matches a bit better. So ultimately, we have a similarity that we researched this to have the best similarity function between graphs in our context. And then we have a symmetry module, so meaning we can go to this module and say, for some RC issue, give me the top most similar RC issues with scores above some score in the past. So we can find similar issues that happened in the past based on one. And with this building block, we can do other things, which are pretty easy to build once you have this. The next part is probability estimation. Let's imagine you have an issue at some point. Then you have initially, you have no clue which one is the root cause. You have 2. So let's say it's 50-50. Then another issue comes in. And you say, has there been a similar issue in the past? Let's say based on the function that they are considered similar enough. Well, you're going to look at it, and you're going to say, based on the 2 new nodes that I have, which one was already a root cause in the past? Well, the top one, not the bottom one. So maybe you give a bit of a different probability distribution. It's not exactly the same numbers that we compute, right? But it's just the idea. Here you can basically have a different probability distribution based on what happened in the past. And what is nice is that this probability distribution, it works even better once people give feedback and you give them incentive to give feedback. Because now what happens if, again, you have an issue, no clue what happened, 50-50, investigation comes in, then the service control center who is handling this is coming back after investigation and say, we have now the business context that you guys don't see, and I know for a fact that it was this one, not the other one. So now we can give 100% and 0% probability distribution because we know it. Meaning that when this happens again, well, the probability distribution can be even more skewed because you have the user feedback now. Right, so that's a bit the next part that basically allowed to, when you have a big graph, to say different distribution, to say, okay, maybe you should look at it first because based on similar issues in the past, etc. So already, this helped already. And then we thought like, okay, can we take this a bit of a step further? What is missing in this big picture? And what is missing is that usually the service control center, DevOps teams, they rely on other things for investigation. They rely usually on post-mortem analysis, comments, investigation. They put stuff in Jira comments, in OneITSM, everywhere in this stuff. And well, you cannot rely only on the graph because it's not like everything is sourced. We always have like some nodes, some backend that is not instrumented, and it was actually this one that was failing. So we cannot just rely on what is in the graph. So we thought, okay, but is it reasonable that we parse everything, like, we force a service control center to give us like the state in some data format about what was root cause? Not really. They're always going to write comments and stuff. So, well, our only hope is, well, let's use AI for this. And what we relied on is RAG. So just the principle of RAG, just as a reminder, so you have a prompt, you have a RAG system, you do some embeddings, you go to the vector database, you have stored other things, you do vector similarity, and then basically you enrich your prompt to the LLM. It's kind of a trick to make the user think that the LLM is answering the question where actually you were already giving the full context and the answer in your question, but the user doesn't know that. And in our context, well, if we apply, it's basically you give an RC issue, we call the graph similarity module to get all the other RC issues, and we pass it to the LLM and we say, what is the root cause in this? Because in each RC issue, there is not only the graph, we can enrich it with the comments of investigators. So now when we pass it to the LLM, we can pass everything and say, what is the root cause? And notice this, that this doesn't require any model training, no MCP, so no security risk, just a simple RAG and a simple function between graphs. All right, let's quickly have a short demo. So I cannot show the best examples because, sometimes it's quite sensitive issues about Switzerland, but let's try to still show one. One is a real one and others are basically fake example just for you. So, for example, this is a graph. You can see here the duration anomalies that were triggered. We have the function health, the component, the resource, and at the end, 2 top business processes like contract takeover and subscription modification. And with all these graphs, basically, you have a nice picture of what was the root cause, what was the impact. And at the bottom, we have here an AI summary. And the AI summary can tell you, well, this issue is a cascading effect based on the same pattern with Circuit 500. And it says, well, we have similar historical pattern. It can tell you basically, here are the links to past similar issues it considered. So now the investigators can both have the graph, look a bit at root cause estimation, and go to the past similar issues and say, okay, maybe something happened there, and we can learn from the past quite easily and see. So this is already quite nice. But for me, this was not the main point of building the LLM. So it's nice that we have this on top. It was not why we built it, because, well, it just describes the graph, right? I mean, it's nice for the hype, but it doesn't provide an added feature that we could have built this without an LLM. But for the next part, we can actually we rely really on the LLM for this. So this is a toy example from test where I myself put a feedback for demo purposes. So here, I put a comment saying, well, I don't know if it's big enough. Yeah. I put, like, the root cause was a MariaDB failure behind proxy.rest. So there is a component. I even mistyped it's lowercase in my comment, and I put, like, let's assume that I know for a fact after investigation that there was a MariaDB that we don't see in the graph because let's say it's not instrumented or for some reason. And I put this as a comment. And then this was in October 2025. Then new issue in January 2026. And I put another comment. And I said, the root cause is still the same MariaDB failure that we had in October. And then let's look at an issue that happened in March this year. There is no comment. There is no feedback. But what is the AI summary telling us? Well, it's telling us, well, the root cause was a MariaDB failure based on similar issues and investigator comments from previous incidents. So it means that the AI summary is able to leverage the comments from investigations. And this is key, because now imagine that at Swisscom we have so many information about the investigation and comments, it would take ages to look at them all. And also, a lot of them are in Swiss German, so like it's even more harder to parse, So here only the LLM can save us. So this is where we are going and how we are leveraging the AI for this. All right, and with this demo, thank you for your attention and happy to answer any question.